In this little portion, we will talk about the synthesis of organohalides, and a big part of the synthesis is free radical reactions, which is how you actually synthesize the organohalides. So in the radical reactions, the first thing we need to kind of talk about is the homolytic cleavage. And homo, if you remember, is equal sharing, and so cleavage is breaking. So in this case, for example, if we take chlorine chlorine molecule, then you can break that bond, and one of the electrons will go to chlorine from that bond, and the other electron will go to the other chlorine. And this kind of a breakage usually happens in presence of some energy, whether it's light or heat. And so once the bond breaks, you end up getting two radicals. And the radicals have an extra electron. They don't have a charge, so no positives, no negatives, okay? But the bond breakage does require energy, which means that the bond energy really plays a role in how these reactions are going to work. So usually there is a table that you can consult to figure out which bond is easier to break and which is harder to break. So for example, HCl is easier to break than HF bond, and we'll go through that table also. The other thing about these reactions is that the radicals are really high in energy, and therefore they're a little bit reactive, which means that you really have to control the reaction so it doesn't get out of hand. Most of the free radical reaction mechanisms that we talk about involve three steps. Initiation, okay, which has an initiator, which means that generates the free radicals. Propagation, and this is really where the reaction takes place. The key thing about the propagation is that it leads to the formation of another free radical. Okay, that's the mark of a propagation reaction. And then finally, termination. Termination is where you actually finish off the reaction. So sometimes the termination requires a terminator, yes, terminator, or a quencher, okay, which means that will stop the reaction. There is one more way that you can stop the reaction. You can think about it, okay? But anyhow, this is how we get started with the radical reaction. So let's look at the radical reactions. There's a whole lot of mechanism involved over here. It's a little bit different kind of mechanism, not like the substitution and elimination reactions we did. There are no carbocations, there is no electrophile, nucleophile, none of that. So a very different kind of a mechanism. So let's start with initiation first. Okay, and in initiation you form radicals. All right, so there's a homolytic cleavage going on for a molecule. Usually you will start with a halogen like chlorine or bromine in order to generate the radical, or you can also start with a peroxide. Peroxide are very good initiators as the oxygen-oxygen bond here is very weak. Okay, and so give it a little bit of energy and it dissociates into two, and you end up getting two alkoxy radicals. All right, so here is a radical and then here is one. So the peroxide may be symmetrical or asymmetric, it doesn't really matter, okay, but that's what happens. And then you can use this peroxy radical, or excuse me, the alkoxy radical that we just formed in order to go on with the reaction, okay, or to generate the actual free radical that you need, because you may not actually use that alkoxy radical for your reaction. You may still need the halide. So now you can use HBr, okay, for your starting, and then you get the halide here, okay, as the free radical. So this is just an initiator that gets it started, and then you form your reagent, okay, that you need, which is the bromine radical. Now, this is bromine, you can also have chlorine, okay, it depends what you're trying to do. Then the next step in the whole series of reactions is propagation, and propagation is where the reaction takes place and then you also generate a radical, okay, in the product. You must have a radical in the product. If you don't have that, that means you have a termination step, okay. And so looking at over here where you have methane, and you're reacting this with a chlorine radical, as in over here that we generated the chlorine radical. Now we are reacting it here with methane. So now you can see that there are 2 or 3 arrows involved here. Okay, so let me go through all of this with you. So once the chlorine radical is there in presence of methane, it will start to abstract this hydrogen, okay, from there, because the CH bond can be broken. There is no other bond to be broken anyway except for the CH bond. So this CH bond then tends to break. Now if you look over here, all of these arrows are single-headed, okay, which means only half-headed. So you're transferring only one electron. So one electron comes from chlorine, one electron comes from the hydrogen. the other electron in the HC bond will go on to the carbon then over here. So which means that you end up generating HCl from the chlorine radical, and then you also form a methyl radical. Okay, now that the methyl radical that is formed, it can react with another chlorine molecule. Okay, just like here when it got started, because everything is all there in the same reaction system. So the chlorine is still present there. So now the methyl radical will do exactly what the chlorine was doing here. Okay, but except with chlorine now. So the methyl radical reacts with the chlorine, with giving its one electron. Chlorine gives one electron to the methyl to form a bond to give chloromethane, and then one of the electron goes to chlorine to give the chlorine radical. Okay, and so this is propagation, because in both cases you end up forming a radical. All right, so that's how we go on to the next step. And then finally we have the termination. The termination is wherever you combine two radicals to form a stable product where there's no radicals. Okay, and that's the key thing in termination. Okay, that you should not have any radicals present. So anything can happen, since everything is happening in all the same reaction system. Anything is possible, which means that if there are two chlorine radicals around, then they can combine to form chlorine. This is more stable than the radical. You can have a chlorine radical with a methyl radical to give chloromethane. You can have the two methyl radicals reacting to give ethane. And so these are all possible steps. Which one is happening? Maybe all of them are happening. Which one can you write? You can write any one of them. Okay, anything is possible. So you can write any of these steps during the reaction or during the termination step. So here is the entire mechanism on one slide. Okay, so let's just go through this really quickly. Here is the initiation step where the chlorine goes through the homolytic cleavage to give two chlorine radicals. And this over here is H-nu. H-nu stands for light energy. This is really the Planck's equation. Okay, over here, H-nu. Nu is frequency, H is Planck's constant. So anyhow, if you take chlorine and you expose it to light energy, really high frequency energy, then it will cleave over here to give the two free radicals. Then we have the propagation steps. In the propagation steps, now you have the chloride radical reacting with methane to give HCl and the methyl radical, which then the methyl radical reacts with the chlorine to give chloromethane, and then you have the chloride radical left over, right? And that goes back again, and the cycle keeps repeating itself. Okay, and so you end up making more and more of the methyl chloride. In case you are wondering if the reaction can be stopped here with the methyl chloride, we'll come back to that. Okay, we will talk about how to control these reactions. In any case, after the propagation steps are the termination steps. Okay, in case of the termination steps, you can take any two radicals that you have written out here in initiation and propagation and combine them to give whatever compounds are forming. Okay, and that's okay. So provided you take any of the radicals that you have just formed. Those are the termination steps. And again, remember, in propagation steps, you must have a free radical in the products. In termination, you cannot have any free radicals, okay, in the product. So here is the overall reaction written out, and there should be energy on the arrow, and so this gives you chloromethane. Okay, and we will talk more about this reaction later on. Let's talk a little bit about the bond energetics, because in case of free radical reactions, all reactions are determined by energy levels, okay, or energies, because you have to break a bond and you have to break it properly. Okay, atoms usually have high energy, all right, in general. When they combine with other atoms, then they release energy and they go down to a lower energy level, because that's where they are more stable, which means that if you need to break those bonds, then you require energy. And so therefore the reverse step is endothermic, okay, which means that you require energy to break a bond. So for example, if you were to break a hydrogen-hydrogen bond, you would need 436 kilojoules per mole, okay, of energy. And for Cl bond, for Cl2, you would require only half of that. So which means that it is easier to break a chlorine bond than a hydrogen bond. So if you're looking for a good initiator for your radical reactions, you're better off choosing chlorine than hydrogen. Okay, so that's how you determine which one to start with, okay, or which radical to start with. Then the other part is about the stability of radical. Which radical will form easily? The first reaction that we just finished, it's very simple because you're starting only with one carbon, so it was only methane. But if you have a longer chain where it is possible for two hydrogen bonds to break, okay, or two hydrogens to break off, either a terminal one or the one in the middle, which means if a terminal breaks, then you'll end up getting a primary radical. If a middle one breaks, then you end up getting a secondary radical. Okay, just like you have for carbocations, primary, secondary, tertiary is the same thing for radicals also. So here you can see the energetics of that reaction. So it takes a lot more energy. I wouldn't say a lot more. It takes more energy to break a primary hydrogen than a secondary hydrogen. Okay, so which means that if it's possible for the molecule, it will get rid of its secondary hydrogen rather than a primary hydrogen. It also tells you then what kind of products you'll be forming, okay, which means that a primary halide is probably not a very likely product in this kind of a reaction, which makes sense because secondary halides, or excuse me, secondary radicals are more stable than primary, just like carbocations, okay, and so it shows that in the energetics also. And here are a list of the bond energies. Now, typically, if you were working in a lab where you were working with all these free radical reactions, then you will have to look at the chart and look carefully and design your synthesis, okay, as to which bond you want to break. So the pink bonds that you see here, those are the ones that are being broken. And you can see which requires the highest energy over here, which is hydrogen-hydrogen bond here, 436. And a higher one for that is actually the methyl hydrogen. Okay, this one is 440. So it requires very much high energy to break. And then the CF bond, very hard to break. Okay, again, fluorine is very electronegative and very small atom. So it binds very well. Okay, but then look at that. With the fluorine, chlorine, bromine, and iodine, it does not require a whole lot of energy to break the iodine bond. Okay, so similarly compare the fluorine, chlorine, and bromine also. Okay, so these are the energies for that. Bromine requires less energy than chlorine also. So usually bromine is a very good initiator for free radical reactions. So in any case, that's how you actually use all of these numbers over here. Okay, and here are the peroxides, by the way. Here is the T-butoxy peroxide, so only 157, okay, not very high energy that is required. So here is hydrogen peroxide, which is also a very common initiator for these reactions. This chart that I gave you over here is a little bit of a comparison of what works best. Okay, so if you have fluorination going on, chlorination, bromination, and iodination, okay, if you have 4 halides that you want to form, which one is going to form easily? Okay, so fluorination is extremely exothermic, and therefore fluorination reactions are very explosive, okay, because if so much energy is coming out, then how do you control it? All right, and so you're probably better off not trying to do these reactions. Okay, so let me do a very broad comparison first. Okay, compare fluorination with iodination. In iodination, you actually need more energy, which means that it is so slow that the reaction does not even occur. All right, so here we have a very explosive reaction, and here we have almost like a no reaction. So which means that we are left with these two. And then you can compare between chlorination and bromination, that chlorination is more exothermic than bromination. Okay, one of the things that you will have to remember from this chapter for sure is that bromination is very, very specific reaction. It's a slow reaction. Chlorination is faster than bromination because it releases a lot more energy. So this is faster reaction, and because it's faster, it really does not have time to control what kind of products it's forming. Bromination, on the other hand, is it's not very, but it's a slow reaction, and because it's slow, you can actually target what kind of products you want to make with bromination. Okay, so which means bromination really is quite good. But if, on the other hand, if you're not really very worried about what kind of chlorination you would need or what kind of substitution you need with chlorine, then go ahead with chlorination. Okay, it's very easy to do, and it's a fantastic fast reaction to do. Bromination is a little bit of a slower reaction, but then it's also a little bit finicky, okay, in how it does. But you get good products with this. Okay, some things that you will not get for chlorination, you get for bromination. Now let's look at some of the other properties of radical reactions. We just covered energetics, in which we see about bond breaking. But now let's get a little bit more into the actual synthesis that's going on. So for example, if you take an alkane with chlorine or bromine and then, expose it to heat or light, what happens? Well, what happens is that it's really very hard to control reaction. As we said, that free radicals are very high in energy, and because they're very high in energy, and they are going through free radical mechanism, they can do anything they want, okay, because you have no control over what's going inside the reaction system that you have. So for example, the reaction that we talked about before, where we had the methane and chlorine, and you provide energy to it, well, we got chloromethane, and that is the reaction we wrote out before with the mechanism. But what is stopping this chloromethane from reacting with another molecule of chlorine to give dichloromethane, which can then react with another molecule of chlorine to give chloroform, which can then react with another molecule of chlorine to give carbon tetrachloride. So which means that it's something not a very good idea to stop at chloromethane, because as soon as you form chloromethane, the whole other series of reactions cannot be stopped. Okay, so it's not a very good way to plan a synthesis, okay, if you wanted to, especially not if you wanted to make chloromethane. If you wanted to make tetrachloromethane, this is fantastic, okay, because all you have to do is give methane, chlorine, heat, and boom, just watch it go all the way to carbon tetrachloride. All right, so that's kind of what happens. Usually what's going to happen is that you have to keep a focus on what I'm asking you to do. Okay, so for example, if I ask you to write me a mechanism of dichloromethane starting from methane, you just keep that focus, okay, on there, and let everything else go. Okay, it's not that everything else is not forming, it's just that I don't want you to worry about it. Okay, and it's not that it doesn't happen, it will happen. It's just that when you're writing the mechanism, just focus on what you're writing. Okay, that's the best thing. The other property that's important for radical reactions is the stability of the radical. We addressed it just a little bit before, 2-3 slides ago, where we talked about the primary radical versus the secondary radical, and the fact that it's easier to make a secondary radical. So that's what this slide is all about. So let's look at the reaction rates first. So here, this first little chart here shows that the tertiary radicals, or the tertiary hydrogen, okay, will react the fastest, and then the primary hydrogen will react the least, okay, and that is because the tertiary radical is the most stable versus the primary radical, just like carbocations. So the stability rate is still the same as for the carbocations as it is with the radicals. However, there are a couple other things that are important here. Okay, and we talked about this before also with carbocations, but it's the same kind of thing here as well. Okay, so for example, allylic radicals, okay, which are the 3 carbon chains over here with 1 double bond, and if we form the radical at this terminal carbon over here, so if this hydrogen goes away, then this allylic radical will be stabilized even more by resonance. Okay, so which means that this electron can move here, and 1 electron will be left over here as a radical. So then this electron can move back and forth between these 2 bonds, and so it's very stable, which means that the allylic radical is even more stable than the tertiary radical because of resonance. Okay, and then the tertiary is more stable than secondary, then primary, then the methyl, and the vinylic is not very stable at all because you can't have extra electrons on already something that is full of electrons, okay, which is the pi bond already. So this is the order of stability, which yes, you must know, okay, so that you can predict what kind of products will be formed. And then there is a case of regioselectivity, which also I kind of mentioned to you a little bit before about bromine and chlorine and how bromine is a little bit more selective because it's a little bit of a slower reaction. So it's a little bit more selective than chlorine is. So for example, let's look at here in the reaction of propane with bromine and chlorine. All right. So if you react propane with bromine, the major product here is 2-bromopropane, which if you think about this, it means it's coming from a secondary radical, okay, over here, and then it adds on to the bromine. And the 1-bromopropane, which is coming from the primary radical. So the major product here is the 2-bromopropane coming from the secondary radical. On the other hand, if we look at propane with chlorine, chlorine is not very specific at all. And because it's so highly reactive, you get almost an equal mixture of the primary halide and the secondary halide. Okay, and that shows you that chlorine is not very specific in its reaction. Okay, and therefore bromine is a preferred choice in case you really want to be careful about what you're making. Or if you have a selectivity of primary, secondary, and tertiary, then you want to use bromine. But if you're not worried about those kind of things, then you use chlorine. All right, and so the regioselectivity is also better for tertiary carbon radical than secondary than primary. Okay. Now, as far as the stereochemistry is concerned, this is also a property, okay, because one of the things that can happen with radical reactions is you can generate chiral centers, okay, and so just like carbocations, carbon radicals will also give you a racemic mixture, okay, because just like carbocations, the carbon radical is also sp2 hybridized, and because it's sp2 hybridized, it's trigonal planar, okay, so this is what it looks like in the intermediate form. So which means that now the bromine can come from either below or it can come from above. And so both can happen. So if it is possible and if you are generating a chiral center, then you will get a racemic mixture, okay, for the product. So again, one has to be careful if you're generating a chiral center or not, because you will get stereoisomers and you will get a racemic mixture. There is no preference of one or the other, because there is no preference for the hybridization. Okay, the radical is sp2 hybridized. A little bit more about the allylic radical, because this is a very nice, interesting reaction. Okay, so first of all, right here is the resonance, okay, that's going on over here. So here is how you will draw the arrows for the allyl radical. And I think you have done this before in one of the chapters that we did about introduction to chemical reactions, all right? But in any case, here we have the radical going on to this carbon-carbon bond. One of the electrons will come here, and one of the electrons will go on to the other carbon. So that's how this carbon gets the radical, and these two electrons make the double bond over here. Okay, so this kind of a movement goes on very fast, and because this movement is very fast, we say that the electrons are delocalized over these three carbons. Okay, so this delocalization leads to very much of a stable radical. Okay, and so one of the reagents that's used a lot for reacting with in an allylic manner is NBS, okay, which is N-bromosuccinimide, and N-bromosuccinimide or NBS will react with alkenes, okay, and in alkenes you don't really see it that way, but if you look at this alkene over here, these two positions are allylic positions, okay. Now remember, the allylic positions will not be in alkanes because alkanes don't have a double bond. So allyl radical is only a property of double bonds. And so this is a cyclic compound, yet you still have the allylic carbons over here, because the point is to have resonance, okay, or to have that 3-carbon chain, okay, that you need to form the resonance. So in case you're looking at the top hydrogens, you have 1, 2, 3 carbon structure. If you're looking at the bottom, it's 1, 2, 3. So these are the allylic positions, okay, in cyclohexene. So which means that if you take cyclohexene and treat it with NBS, which is N-bromosuccinimide, and use the free radical mechanism, then you will get addition at or substitution at the allylic position. Okay, and then you can of course do another elimination to get an alkene, but that's not so important right now. What's important is that if you're adding bromine, you're not really getting the addition on the alkene, you're actually getting substitution on the allylic position. That is the purpose of this reaction, okay, because if you have alkenes, then you can also get addition reactions with bromine. All right, so if you don't want addition reaction with bromine, you want a substitution reaction, then you use NBS, and then of course you use the free radical mechanism, which means that you need to have some sort of energy over here. Okay, so if you wanted to make a dialkene, this is the best way to do it. Okay. All right, so here's another example, and this is of a straight chain. So now here the allylic position is right here. Okay, so this is the allylic position, and that's where you get the bromine. Here is the allylic position, and this is where you get the bromine. Why do we get this one as the major product and not this one? I'll give you a second to think about it. Why is this the major product? This is the major product because in this case, the radical is actually inside. It's like a secondary halide, okay, or excuse me, a secondary radical, okay? Whereas if it was outside over here, it would be like a primary carbon, okay, a radical. So that's why this bromine over here on the outside, this is the more, this is the major product. We did not have this issue in the cyclic compound because here we don't have the problem of primary or secondary. Both of these carbons are equivalent. So another phenomena that happens in free radical reactions is chain reactions. Chain reaction is another name for propagation steps, okay, where you form a free radical in the product. But as the name sounds, okay, chain reaction, it means that the reaction goes on and on and on, okay, so it's kind of very hard to stop. And then the other thing about radical reactions is because radical reactions are very high in energy, it's sometimes a little bit hard to control, okay, what's going on. So these reactions where propagation is going on is called a chain reaction. So the best way to stop a chain reaction from happening is by adding a terminator or a quencher, okay, which removes these radicals, or yes, you can remove the energy source, okay, and so that will then stop the chain reaction from happening. But chain reaction is a name that is given specifically for free radical reactions. A little bit about the addition of bromine on alkenes. Okay, we talked about the allyl addition, and the allyl is a little bit different because the reaction is not really happening on the alkene. The reaction in case of allyl is happening outside the alkene. All right, so you can also have addition reactions with free radical reactions. So far, we have done only substitution reactions, okay, with free radical reactions. So now we're going on to the addition reactions on alkenes. So as you know from before, okay, what we've done with alkenes is that if you have an asymmetric alkene, that you end up getting a Markovnikov addition. Okay, so for example, if you take 2-methylpropene, where this alkene is asymmetric, okay, and so in this case, if you add HBr to this, the hydrogen will go to the carbon with more hydrogen, and the bromine will go to the carbon that has more substituents, okay, which is exactly what happened over here. So the bromine has gone to the carbon with more substituents, and the hydrogen has gone to the carbon with more hydrogens. Okay, so this is the major, in fact, this is the only product possible. Okay, however, when you take the same compound, 2-methylpropene, treat it with HBr in presence of peroxides, now you get a different kind of product. Okay, so now in this case, you would get the bromine where the hydrogen should have gone and the hydrogen where the bromine should have gone. Okay, so bromine has gone to the carbon with more hydrogens. So now this is anti-Markovnikov's product. Okay, and so this is something that happens when you add peroxides. Okay, so we have to look at the mechanism for this reaction, okay, in order to understand what's going on. And by the way, before I go on, just a little mention over here, HCl and HI, they're only Markovnikov's addition. It's only bromine that's a little bit unique. And as I said to you before also, that bromine is a little bit unique as far as. So here is the mechanism of the reaction, okay, for adding HBr. So you start the reaction, okay, which is this one over here. This is the initiation. So you start with the alkoxy radicals. The alkoxy radicals then will go ahead and abstract this hydrogen and give the bromine radical. Okay, so once the bromine radical is formed, now this will react with the 2-methylpropene. Now, once this is reacting, you can form two radicals. You can form a radical here at the primary carbon, or you can form the radical here at the tertiary carbon. So guess which one is more stable? Obviously, yes, the tertiary radical. So if the tertiary radical is more common and more stable, this is what it's going to form. Okay, so which means that now the bromine has already added to the carbon with the more hydrogen, and it added there because a more stable tertiary radical is formed. Okay, so then this tertiary radical will pick up a hydrogen and you end up getting a hydrogen over here. So here is how the HBr adds in an anti-Markovnikov fashion just because of the mechanism. Now, if you remember, the mechanism for addition of HBr for alkene without the peroxides was different. Okay, it was a carbocation mechanism, and because it was an acid-base reaction, the double bond picked up the hydrogen first. Here, the double bond is picking up the bromine first. Okay, so here where it was picking the hydrogen first, the hydrogen went to the carbon with more hydrogen. But here, because the double bond is picking up the bromine first, the bromine goes to the carbon with more hydrogens. Okay, but otherwise you're still forming the more stable radical. In that case, it was the carbocation, and here it is the radical. Okay, I hope you can see the difference between how the two mechanisms are working. But again, these are little things that you have to remember. Okay, what gives you Markovnikov product and what gives you the anti-Markovnikov product. So finally, for this part of radical reactions or alkyl halides, you need to know all the synthesis of alkyl halides from alkenes, alkynes, and then of course from alkanes, which is what this portion was really all about. And from alkanes, you need to know the free radical reactions on alkanes to give the alkyl halides. All these different things about the homolytic cleavage, initiation, propagation, termination, the stability of radicals, you should be able to predict that. Regarding the energetics of the reaction, I need you to understand the basic fundamentals of how the bond breaks and forms, the exothermic and endothermic. I may not actually have you work out the energetics of a reaction, okay? Because typically that's what happens in free radical reactions. You have to actually calculate if the reaction is going to be exothermic or endothermic, or if it's going to even work or not, okay? But we're not going to do that. We're going to focus more on synthesis. And then you need to know about the regioselectivity of bromine, okay, as we talked about with NBS, and then we also talked about that with the addition reaction of alkenes, then the allyl radical, and then just the concept of chain reaction, okay, so you understand what it means.